Hello, welcome back. We are discussing Chapter 2, Lesson 3, using deductive reasoning to verify conjectures. So the warm-up today is to identify the hypothesis and conclusion of each conditional. Now, usually I'd have you do these on your own, but these conditional statements are a little different. They don't have those key words of if and then, and so it just makes it a little bit more difficult. So I think we're just going to do these ones together just so we kind of get the hang of it. So the first one says a mapping that is a reflection is a type of transformation. So a mapping that is a reflection is a type of transformation. So we need to identify the hypothesis, remember that's P, and the conclusion, which is Q. So we have two different types of things going on. We got the reflection and then we got the transformation. And a mapping, that's probably what we're going to be using in both of the sentences. So the hypothesis is a mapping that is a reflection. Which would make the conclusion have type of transformation in it. Well, what is a type of transformation? A mapping is a type of transformation. So we would say the mapping is a type of transformation. Okay, and then if I wanted to say like a conditional like what we're used to, I would say if a mapping is a reflection, oh, it needs an L. It shouldn't be a mapping that, it should just be is, sorry about that. A mapping is a reflection. So if a mapping is a reflection, then the mapping is a type of transformation. So that is kind of more of the conditional statements that we're used to. So let's look at this one. The quotient of two negative numbers is positive. Okay, so we have three pieces of information. We have quotient, we have two negative numbers, and we have positive. I think I would group the quotient and positive, those two together. And two negative numbers, that would have to deal with the hypothesis. So we're just going to use two numbers are negative. That's going to be our hypothesis. Two numbers are negative. Then two numbers are negative. The quotient is positive would be our conclusion. And you can see if we put if and then, if two numbers are negative, then the quotient is positive, and it makes sense. So, all right, let's look at the third here. It says determine if the conditional, if x is a number, then the absolute value is greater than 0. I'm going to put missing quotations, is true. So if it's false, give a counterexample. So let's just go ahead and think about that. If x is a number, then the absolute value of x is greater than 0. So whenever we're dealing with something like this, we kind of want to look at all the different types of possibilities. Okay, what could x be? Well, x could be a positive number, x could be a fraction, x could be a negative number. You know, all those different types of things. Okay, well, what would happen if x was a positive number? So positive like positive 2. So if we had the absolute value of 2, is that greater than 0? I don't know. Absolute value of 2 is 2, and 2 is greater than 0, so that works. Okay. Would it work with another positive number? What about the absolute value of 10? Is the absolute value of 10 greater than 0? Yeah, the absolute value of 10 is 10, and greater than 0. So we want to think, okay, is there any positive number that this wouldn't work for? And I think this would be true for all positive numbers. Well, what about fractions? What about 1/2? The absolute value of 1/2. Is that greater than 0? Well, the absolute value of 1/2 is just 1/2, and yes, 1/2 is greater than 0. Okay, so it seems like that works for all positive numbers and fractions as well. So let's think about negative numbers. What if it was the absolute value of -4? Is that greater than 0? Well, the absolute value of negative 4 would be 4, which is greater than 0. So really, any negative number, once you take the absolute value, it's going to become a positive number, which is always going to be greater than 0. And what about if there was like a negative fraction or something? So like negative 1/2. Is that greater than 0? Well, negative absolute value of negative 1/2 would be a positive 1/2, and then, yeah, that would be greater than 0. Okay, so what you want to think about, so far this looks like this conditional is true. Is there anything that would make it false? Any number out there? Can you think of one? We talked about all the positive numbers, talked about all the negative numbers, talked about the fractions. Decimals, would decimal have an effect? Well, what if x is equal to 0? Okay, if x was equal to 0, then we'd have the absolute value of 0, and the absolute value of 0 would just be 0. And is 0 greater than 0? No, that is false. So that is our counter example. So this is not a true conditional. This is a false conditional, and well, this conditional is false. And the counter example would be x equaling 0. Okie doke. Perfecto. All right, let's keep moving on. So we've talked a lot about inductive reasoning in the last section, but now we're going to talk about deductive reasoning. Deductive reasoning is the process of using logic to draw conclusions from given facts, definitions, and properties. The process of using logic to draw conclusions from given facts, definitions, and properties. So that's quite a bit there, given. So you're using logic to draw conclusions from given facts, okay, from given definitions and properties. That is deductive reasoning. So the first bit in this chapter, we talked about inductive reasoning. Remember, inductive reasoning, that was like if we're just out there observing the world and we see a pattern, or we're looking at a series of numbers and we're like, oh, they're all increased by 3, so therefore I see that pattern, and my inductive reasoning would be the next number would also be increased by 3. So that was inductive reasoning. This section is about deductive. It's using logic to draw conclusions from given facts, definitions, and properties. So what we're going to do is we're going to look at these next examples, and we're just going to determine whether is the conclusion a result of inductive or deductive reasoning. So we're just trying to differentiate between the two. Okay, inductive reasoning, which is kind of like looking at patterns, and deductive reasoning, which is using given facts, definitions, and properties. So here we go. There's a myth that you can balance an egg on its end only on the spring equinox. A person was able to balance an egg on July 8th, September 21st, and December 19th. Therefore, this myth is false. So is that a result of inductive or deductive reasoning? Is it looking at patterns, or is it drawing conclusions from given facts, definitions, and properties? Well, in this instance, and I think it's always just easiest to figure out, to tell the difference just by looking at examples and going through them. So here, what they're doing is they're performing experiments on July 8th, September 21st, and December 19th. And so they're kind of doing an experiment and then using reasoning based on the results of that experiment, which would be kind of like trying to see a pattern. So this would be inductive reasoning. Okay, let's look at the next one. Number 2, there is a myth that the Great Wall of China is the only man-made object visible from the moon. The Great Wall is barely visible in photographs taken from 180 miles above the Earth. The moon is about 237,000 miles from the Earth. Therefore, the myth cannot be true. Okay, so I'm going to read that again. There is a myth that the Great Wall of China is the only man-made object visible from the moon. Okay, so they're saying that the Great Wall of China is visible from the moon. Okay, then it says the Great Wall is barely visible in photographs taken from 180 miles above the Earth. The moon is about 237,000 miles from the Earth. Therefore, the myth cannot be true. So this is an example of inductive or deductive reasoning. This one is using deductive reasoning because it's using logic to draw conclusions. It's basically saying, hey, you know, you can't even see the Great Wall of China 180 miles above the Earth. It's barely visible. So there's no way it's going to be visible 237,000 miles from the Earth. Okay? So it's given facts and drawing conclusions using logic. So this would be deductive reasoning. Okay, let's look at the next example here. Okay, there's a myth that an eel skin wallet will demagnetize credit cards because the skin of electric eels used to make the wallet holds an electric charge. However, eel skin products are not made from electric eels. Therefore, the myth cannot be true. Is this conclusion a result of inductive or deductive reasoning? Okay, so let's read it again. There's a myth that the eel skin wallet will demagnetize credit cards because the skin of electric eels used to make wallets holds an electric charge. Okay. However, eel skin products are not made from electric eels. Therefore, the myth cannot be true. So, this is actually using, what do you think, inductive or deductive reasoning? This is using deductive reasoning because it's using facts. Okay, yes, it says that electric eels hold an electric charge. However, it's saying any products used with eel skin are not made from electric eels. So therefore, this myth cannot be true because they're not even using electric eels. They're using some other type of eels. So this is just another example of using logic to draw conclusions. Okay, this would be facts. All right, so they're not even, you know, all these eel skin products aren't even made from electric eels. So there's no way it can demagnetize credit cards. So this is another example of deductive reasoning. So helpfully going through those three examples, you're able to kind of see the difference between inductive reasoning and deductive reasoning. All right, I'll see you back in a little bit for example 2.